Have you ever stared at a problem that's so massive, so huge, you have absolutely no idea where to even start? Well, today I'm going to show you a powerful thinking tool that physicists and engineers use all the time to tackle those seemingly impossible questions. It's called the art of the guesstimate, and trust me, it's a game changer.
So let's just dive right in with a whopper. How high would a stack of $1 trillion be? And let's say it's all in $100 bills. What do you think? A couple of inches? As tall as a car? Maybe a skyscraper? Right now, it feels like a total shot in the dark. But by the end of this, you're going to have a surprisingly solid answer.
So to even begin to answer that question, we need a completely new way of thinking. This is where we introduce the idea of scientific approximation. Now, this isn't just random guessing. It's a really powerful method, sometimes called a Fermi problem, and it's kind of like a secret weapon for breaking down these enormous, complex problems into pieces we can actually work with.
Okay, so what is an approximation, really? Well, the key thing to remember is right there in the definition. It's an estimated value, sure, but, and this is the important part, it's based on prior experience and reasoning. It's a guesstimate, but it's a guesstimate that's guided by logic. That's the secret sauce.
You might be wondering, why would a scientist, guess at all? Well, it's actually a super strategic process. By making a quick, reasoned estimate, they can immediately see if an idea is even in the realm of possibility. It lets them filter out scenarios that are just physically impossible. It helps them challenge their own assumptions and figure out, okay, where should I actually focus my energy before they waste a ton of time on a detailed calculation? It's all about getting into the right ballpark from the get-go.
To get a feel for how this works, let's put the $1 trillion on hold for just a second and start with something a little more down to earth. How could we figure out the height of a tall building if we don't have a giant measuring tape?
The process is actually beautiful in its simplicity. First, you start with something you already know. Let's say for step 1, we know the average adult is roughly 2 meters tall. Okay, easy enough. For step 2, we connect that to our problem. We can guess that one story of a building is probably about the height of 2 people standing on top of each other. Then for step 3, we just scale it up. If our building has 39 stories, we do the math.
And boom, there you have it. You get about 156 meters. Now, is that the exact height down to the last centimeter? Of course not. But are we in the right ballpark? Absolutely. We just went from I have no idea to having a really reasonable, quantitative feel for how tall that building is. See how powerful that is?
All right, warm-up's over. Now that we've got the basic idea down, it's time to go back to the main event. Let's apply our new skills to that mind-bending question about the $1 trillion.
So, remember those first guesses? Somebody says 3 inches, another friend says 10 feet. Those are just pure guesstimates, right? Just wild stabs in the dark. Let's see if we can do better by building a careful, calculated approximation.
Okay, here's our game plan. We're going to break this down piece by piece just like we did with the building. We'll start small, with the volume of a single stack of bills. Then, we figure out just how many of those stacks we're dealing with. After that, we calculate the total volume, and finally, we'll imagine spreading it all out over a football field and see how high it goes. It's a logical path.
All right, first things first. We need a basic building block. A US dollar bill is about 6 inches long and 3 inches wide. A fresh stack of 100 bills is about a ½ inch thick. So you multiply all that together, and you get a volume of about 9 cubic inches for one stack of $10,000. That's our starting point.
And now for the really big number. A trillion is 1,000 billion. So if we take our $1 trillion and divide it by the $10,000 in each stack, we find out we are dealing with 100 million stacks of cash. Just let that number sink in for a second. 100 million. It's an insane number, but now it's a number we can actually work with.
So there we have it. We have 100 million stacks, and each one takes up 9 cubic inches of space, and we're going to spread them all evenly over a football field. We have all the pieces of the puzzle. So before I show you the answer, just pause for a second. What's your guesstimate now? Is it going to be closer to that 3 inches or closer to 10 feet? Go ahead, lock in your answer.
Okay, you got your guess? Let's see how you did. When you take the total volume of all that money, which is a whopping 900 million cubic inches, and you divide it by the area of a football field, you get a height of about 100 inches. And 100 inches is right around 8 feet. So let's look back at those original guesses. 3 inches was, well, it was way, way off. Totally impossible. But the guess of 10 feet? Wow, that's actually really close. It was right in the ballpark. And this perfectly shows the difference between just a wild guess and a reasoned one.
And this gets us right to the heart of the matter. The whole point of this, the power of approximation, isn't about getting the perfect answer. It's about developing the skill to get a reasonable answer, to quickly figure out if an idea is even possible.
The source material asks this question, and it really is the key takeaway. What's the difference between a rough guesstimate and a calculated approximation? Well, the difference is everything. One can be totally wrong, while the other, even using estimated numbers, can get you incredibly close to the actual truth.
And that is exactly why this is such a critical skill for scientists and engineers, and really for anyone who wants to think more clearly about the world. It's a tool that lets you throw out the ideas that are just plain impossible so you can focus your time and energy on the ones that might actually work. It's your built-in reality check.
So now it's your turn to try. Here's a classic Fermi problem for you. How many times does a human heart beat in an average lifetime? You have the tools now. Start with what you know,